Are you there, please?
Should I go on now?
Yeah, can start now.
All right, I'll be sharing my screen right
Yeah,
about now.
yeah, your video.
I'll share my video too. So I think you should be able to see my screen number.
Yes, yes.
Okay. I'm trying to share my video. Okay. This morning I'll be talking on Python and scientific libraries. The table of content, getting started with Python, scientific libraries, vectorization, and that's the conclusion. So Python is a powerful programming language used in a variety of professions, ranging from data science to web development. It's in the top 10 for most popular and most loved technologies, according to Stack Overflow's 2016 developer survey, making it a relatively friendly language. We should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil. So what this means is premature optimization means incorrect data are why a lot of things are happening the way they are happening because we are not having correct data to do what we want to do. People are faking data. Nobody is doing research to be very, very sure. So at times that some of us want to talk, we'll be like, we'll just guess. It's 7% of girls are very, very stupid. That is a guess. We just feel like because girls are stupid in normal day, we should now say it's 7% of girls are very, very stupid. So premature optimization is the root of all evil. So getting started with Python. That's why I'm going to be teaching Python and scientific library so that we can understand so that we don't have to be using premature optimizations for most of our work. We can be using Python scientific libraries to get the accurate data for things we want to work on. Getting started with Python. Python is an integrated programming language that allows you to do almost anything with a compiled language like C, C Sharp, Fortran without requiring all the complexities. Python is extremely popular for scientific computing due to such factors as the accessible and flexible nature of the language itself, the huge range of high quality scientific libraries now available, the fact that the language and libraries are open source, the recent sort of interest in using Python for machine learning and artificial intelligence. So for a lot of things, Python is already opening up itself to be used in almost anything. Python for machine learning, Python for scientific computing, Python for artificial intelligence, Python for data science. But what I'm talking about today is Python with scientific libraries, using scientific libraries for scientific computing, like cosine, tan, and the rest, drawing graphs with Python. In this lecture, I give a short overview of scientific computing in Python, addressing the following questions. What are the relative strengths and weaknesses of Python for these tasks? What are the main elements of scientific Python ecosystem? And how is the situation changing over time? So defining the concept of Python. Python is an object-oriented programming such that is object-oriented whereby you can have as many objects assigned to a class. You can what that means is you don't have to have to be writing a code repeatedly to if you want to use like 10 times, you have to write it 10 times to use it. You can just write it once, then you now assign out like 100 objects to this single code. That's what I mean by object oriented programming. Easy to learn and use. Python is a straightforward programming language. The syntax are easy. You have print. They are, if you want to learn the syntax, it's very very easy for you to use. It's readable also. Um, print, break, if statement, for loop. There are things that we can easily understand. It's dynamic typing. They use actual English. They don't use complex grammars and the rest to in Python. Then it is interpreted and interactive. Like I already said, it is easy to use. That it's very very readable. That's meaning of interpreted and interactive. It's very very readable. Then I'm talking on scientific libraries. The role of scientific libraries. One obvious reason we use scientific libraries is because they implement routines we want to use. For example, it's almost always better to use an existing routine for root find and to write a new one from scratch. I already explained that here when I said Python is object oriented, it's object oriented, so that we don't have to be rewriting code every time, we don't have to write code every time when we want to use a particular code. All we can just do is write the code and then we assign an object to the code every time we want to use the code. That's the best way. So for standard algorithms, efficiency is maximized if the community can coordinate on a common set of implementations written by experts and tuned by users to be as fast as robust as possible. But this is not the only reason that we use Python scientific libraries. Another is that pure Python, while flexible and elegant, is not fast. Yeah, I'll get to that during the Python alone is not fast. So they have to write scientific libraries. So we need libraries that are designed to accelerate execution of Python codes. As well, see below there are now Python libraries that can do extremely well. So in terms of popularity, the biggest four in the world of scientific Python libraries are NumPy, we have SciPy, we have Matplotlib, and we have Pandas. For us, there's another relatively new library that will also be essential for American computing. That is Number and SymPy. So what is NumPy? NumPy forms the foundations by providing a basic array data type. Think of vectors and matrix and functions for acting on these arrays, e.g., matrix multiplication. So when you are working with NumPy, you have to use it works with matrix. So if you know a little thing about matrix, NumPy would not be that much of a problem to you to use. Then we have SciPy. SciPy builds on NumPy by adding the kinds of numerical methods that are routinely used in science: interpolation, optimization, root finding. So when you want to use square roots and you want to find the root of some things, you use SciPy. No, NumPy is basically have like two two to five tools inside of it. Then SciPy picked up from where NumPy stopped and added more tools into the toolbox. That's what's new. So some of NumPy functions are already inside SciPy. Just that SciPy is a more advanced version of the NumPy. The Matplotlib is used to generate figures within a focus and plotting data stored in number. Matplotlib, as the name says, plots. That means it is for plotting graphs. Once you are done with writing your code, we want to plot graphs, the best for you to use is Matplotlib. Then we have Pandas. Pandas provide high performance, easy to use data structures. You use Pandas when you want to read when you want to read data structures, when you want to manipulate data structures. Pandas is the most used for data structure. Then we have Number. Like I said, that this Number and SymPy, they are the two new type of scientific libraries. Number accelerates execution via JIT compilation. We will learn about this soon. SymPy is a Python library for symbolic mathematics. It aims to become a full-featured computer algebra system while keeping the code as simple as possible. So when we want to work with a couple of algebras, we want to work with dy dx, a couple of derivative. I think they call it derivative. You'll be using SymPy. So vectorization. This is a clear method. There's a clear method called virtualization that can be used to speed up high-level languages in numerical applications. The key idea is to send array processing operations in batch to precompiled and efficient native machine code. The machine code itself is typically compiled from carefully optimized C or Fortran. For example, when working in a high-level language, the operation of inverting a large matrix can be subcontracted to efficient machine code that is precompiled for this purpose and supplied to users as part of a package. It says when you're working with the high level language, that means once you want to do when you're working something like Python, I want to work with some, you want to do some scientific computing. Using normal Python is going to be taking time. So that they've now made a precompiled package that makes it um easier for users to use, so users can be able to um users can write scientific codes very well with it. This clever idea dates back to MATLAB, which uses vectorization extensively. Vectorization can greatly accelerate many numerical computations, but not all, as we shall see. Let's see how vectorization works in Python using NumPy. Let's use NumPy as one of our testing code. So first, we need to import. In Python, we use the word import random, import NumPy as NP, import Quanticon as QE. So let us try some non-vectorized code, which is a native Python loop. This for I in range n is what we call a Python loop. And when we are writing in Python, when we are dealing with something like 1 million, this is 1 million. Instead of comma, we use underscores because we don't use comma in when we are renaming the variable. We use underscore instead of comma. If you don't want to write everything together, you can use an underscore because it doesn't take commas. So let's try some non-vectorized code, which is the native Python loop to generate square, then sum a large number of random variables. Then so we're looping through range 1 million. So it's going to be counting within 1 and 1 million. So x equals to random the uniform within 0 and 1. It picks from anything. Then y plus or equals to x raised to power 2. Do you understand this? This one is supposed to be I, not 1. I made a mistake here. So uniform 0 and I. So it picks any random number from this place. Then it now says x. That is the number raised to power 2. That's what it's called. You now be adding it to y. If you print y, it's going to give us some random thing, but it's a whole lot. When we go on, I'll show you the code. The following vectorized code achieves the same thing using NumPy. This is just a normal Python code. This is using the scientific library, which is called NumPy. That's what we imported here. NumPy as NP. That's why we have np.random.uniform. Then 0, 1, and n. That is anything random here. Then y equals to np.sum. Over here, I said y plus or equals to x raised to power 2. Y equals to numpy dot add x. This is the x raised to power 2. Then why using the loop? It's ran in 437 seconds. But while using the library, it's ran in 17.3 seconds. So we see that using scientific library is way more faster than using the usual loop. Imagine we have to run this thing up to like, let me say like 10 times. This one would have run 10 times before this one can even run once. If you're even going to run like 30 times, this one would have gone 30 times or 20 times before this one can even run once. So that is why we have scientific libraries that Python have provided for us. As you can see, the second code block runs much faster. Why? The second code block breaks the loop down into 3 basic operations: draw and uniform, square them, then sum them. This one does the one. Why this one keeps going in bits for 1 million times? After it has gone to this place, it starts again. It goes in circles for 1 million times. In circles, just keeps going and going and going and going for 1 million times. They are sent as batch operations to optimize machine code. Apart from monitor overheads associated with sending data back and forth, the result is C or Fortran-like speed. When we use batch operations on arrays like this, we see that the code is vectorized. This is what they call a vectorized code because it has already been part of a package. This is what I call a package. We just assigned this to this numpy package. We assign S to it. This numpy is already a package. We imported the package, imports MP as numpy. That's why we already assigned. I said that when we have a package, we get the package and we assign as many times. We can assign as up to 1 million things for one. This one we only assign only one because it can perform the portion of 1 million things inside one. Vectorized code is typically fast and efficient. It is also surprisingly flexible in this sense that many operations can be vectorized. So many functions provided by NumPy are so-called universal func. That's what they call unfunc. This means that they map scalars into scalars as expected, and they map arrays into arrays as expected. I'm sure some of us, when we were in school, we did follow maths or we did mathematics in general, we were talking about cosine, tan, and the rest. So we can use the same NumPy for cosine. Once we say NumPy dot cosine 1, we get the original cosine value. Then we say NumPy dot cosine. Inside it now have NumPy dot line space. We're trying to manipulate through 0, 1, and 3. So the 0 is here, then this is the 1, and this is the 3. So we have their codes there respectively. So I'll be trying to use this. So I'll be using matplotlib for this part. I want to use matplotlib to plot this graph. This is a mathematical function. By exploiting unfuncs, many operations can be vectorized. For example, consider the problem of maximizing a function f. This is the function f of two variables x and y. So this is like saying f open brackets x, well that's fx comma fy equals to then the cosine of x raised to power 2 plus y raised to power 2 divided by 1 plus x raised to power 2 plus y raised to power 2. And a equals to 3 over the square minus a comma a times minus a comma a. For f, a, let's choose, for f, let us choose a equals to 3. That means f equals to 3 here. So this is writing the code for the for this function, this mathematical function that we see here. Instead of calculating the code manually, we can use Python, NumPy, and the matplotlib to plot the graph, to run the code and see what we have. So we are defining f, right? Fxy equals to this. So cosine x raised to power 2 plus y raised to power 2. That's what we have here. Cosine x raised to power 2 plus y raised to power 2 divided by 1 plus x raised to power 2 plus y raised to power 2 divided by 1 plus x raised to power 2 plus y raised to power 2. So we are trying to run this code. X grid equals to numpy dot line space minus 3, 3, and 50. Y grid, what this means is this minus 3 and 3, they are the part of the graphs. This is minus 3 and this is 3. Then 50 is supposed to be the size, length size, how big you want it to be. Then we have y grid equals to x grid. Xy equals to numpy dot mesh grid. We are meshing this x grid. That's why we have x grid here. And y grid, we have, this is the y axis. Instead of y axis, they use x and y grid here. Then figure, plots. I already imported plots here, matplotlib as plt. So plot figure size 10 over 8. Axis figure dot add subplots 111. Let me not bore you with this whole band. Plots x, y, then f. We are calling this function fxy. That's what we call there. Then we set the X label, we set the Y label. The way we said plot does show, it give us this exact. This is there is no way we could have even drawn this with our hand, making it look this very accurate. There is no way we would have drawn it, making it look this beautiful and it's accurate with our hand. But with Matplotlib and Python, we can do much more of than drawing graphs and just writing codes and doing calculations. We can draw beautiful graphs with them. Then in conclusion, the Python ecosystem contains a mature and still evolving assemblage of competition tools for working science. The Python scientific library is not done yet. Libraries are coming up every day. New libraries are coming out every day, every day, every day. Scientists are flocking to Python in large numbers due to Python's inter interoperability with other language, batteries included, and third-party modules for nearly everything you want to do. Almost everything. Simplicity and dynamic, open air codes is real states to science. The scientific Python community is growing and libraries are constantly being developed. The communities, I told you, libraries are coming up every time, every time, every time. Python is not done with creating libraries. The open source development community keeps to the basic tenets of scientific research more so than any other community. These tenets are peer review, skepticism, transparency, attribute, accountability, collaboration, and impact. That's why the open source people they like working with Python because of all of these things. There's a wider community of Python programmers who are not scientists and want to contribute to the impact of Python on science and the world and issues that they believe in. To twist the words of Perry Greenwood over so slightly. Thank you, everyone. That's about my presentation. Any question, please? Any question, please? Can anybody hear me? Yeah, I can hear you, Matthew. Good morning.
Good morning. I want to ask if Python can be used for mobile dev.
No, I didn't say it could be used for. I said it could be. I didn't mention mobile. I said it could be used for a lot of things, and Python is not sleeping yet. I didn't say it could be used for. I said machine learning, data science. I think it could be used for a couple of web desktop apps also. That's when we use GUI, graphic user interface. GM.
Right, thank you.
Okay. Any other question, please?
Hello, can you hear me?
Yes, I can hear you.
Okay. The other time you're talking about using the coding to design something like graphic design.
It's used for designing to plotting graphs.
Okay,
Something like
graphs.
this.
Okay.
Yes.
Okay. Okay, no problem. That's what I'm said to check.
Okay. Any other question? Any other? Any other question? Anybody? Samuel, I'm done. Nobody's asking any question. Samuel,
Sorry. Good morning. We're
good
having
morning.
network issue.
No,
So
I'm
yeah,
done. I'm done. Yes.
You're done. Okay. How do I frame? I don't think you've read. It's
You
not
said
frame.
what?
Have you asked your questions?
Yes, they have asked me and I've answered their questions.
Okay, what's that?
You said what?
I said, who answered your question?
Victor and Matthew asked me questions.
Okay, Victor. I think someone just joining us. Okay. So the thing is, can you just kind of do a recap since you are the only one available? Okay.
I should go from beginning.
Yeah, just a recap. You understand?
Okay, let me share my
Okay.
screen again.
Most of the people who stay in the location have network issues. So can you do a recap so we can benefit from what you share?
Okay, so in the beginning I gave this quote by Donald Knuth. He said, "We should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil." What this thing means is most of us we are not even very, very sure what we're talking about, but because we just feel it should be so, we'll just go and present incorrect data. That's what premature optimization is. Incorrect data. That's why a lot of things are happening the way they are. Because someone just come there because they don't like girls, and they'll be like 97% of girls are very, very stupid because they've met like about two girls who are stupid. They feel like all girls are also stupid too. So that's it. That can also cause enmity between girls and the person. Somebody saying something.
Please, can you say something?
Not really, but your example is kind of funny though.
The example is funny. Well, I'm just giving an example. My bad if it's hurting. I don't plan to hurt anybody with the example, please.
Wait, you just got that story.
What?
You just got a story.
I'm just giving an example why people used to have issue with each other. That the
All right.
data is not correct. The guy just feel because he has met like two girls who doesn't have sense. He feels every girl don't have sense. So that can be causing enmity between he and a couple of people. That's what I mean by premature optimization is the root of all evil. So over
Okay.
here, I spoke on Python scientific libraries that we have NumPy, we have SciPy, we have Matplotlib, we have Pandas, we have Number, and we have SymPy. And okay, NumPy is basically used for arrays. You can use NumPy for arrays. NumPy for why SciPy built on NumPy. Like let's assume NumPy is a toolbox of 5 tools. SciPy went and got the toolbox and added about like 5 other toolbox into the toolbox. 5 other tools inside the toolbox, making SciPy have more tools than NumPy. That's SciPy. The Matplotlib is basically used for drawing graphs, for plotting graphs, and the rest. Then we have Pandas for breaking into data, manipulating data, and the likes. We have Number, which is a new scientific library. Why SymPy is basically mostly used for algebra equations. But it's used for algebra equations. It's used for dy dx. If I don't know if someone knows what dy dx is, derivatives and the likes. Then vectorization. So over here I spoke on vectorization is simply saying there are a couple of Python libraries that have already been in place for us to write our codes faster. Without using vectorization, our codes will be slower. But with vectorization, with the built-in Python libraries, our codes will be running faster than the usual. So first, we do some imports. We import NumPy. Okay, let me just go. This is normal Python code. We want to run this code 1 million times. This is 1 million. We use underscore instead of comma in programming because we can't use comma to name a variable. So this is, we want to run this 1 million times. And with the vectorized code, we run the same 1 million times. Then let us now look how long. Using the normal loop, it took us 437 seconds to run the code. while using a vectorized code, it took us 17.3 seconds to run the code. That means if I'm supposed to run this code 10 times, this one would run 10 times, but this one can even finish once. This one would even run 20 times before we can even go through this one once. So that's why vectorization makes things faster. And then we can use scientific libraries. Some of us know what cosine, tan, and a couple of things are in our mathematics formula table. So cosine of 1, this is it. We can also get our cosine from numpy. Numpy dot cosine, we have 1. So we use numpy dot tan, we have 1.0. Numpy dot cos, this number, it gives us the. So I give an example of how I plotted the graph for this mathematical function. So we have, for example, we have a function f of 2 variables, x and y, over the square minus a plus a times minus a and a. So we'll be plotting this graph. So this is the code. X, you are saying something. Okay. Over here we have. Are you trying to say something, please? Okay, you are saying. Yeah, I'll just go on. So we have cosine of x raised power 2.
Abubakar, are you saying something?
We have x raised to power 2. Okay, where they have y, f in brackets xy, then the cosine x raised to power 2 plus y raised to power 2 divided by 1. That's what we have here. Divided by 1 plus x raised to power 2 plus y raised to power 2. That's what we have here. That's what we have here also. So I'm trying to plot the graph for this mathematical function. So x grid is, that means y axis, non-prime the line space, minus 3, 3, and 50 supposed to be the size. So we have minus 3 here and we have 3 here. Then we have y grid equals to x grid. That means the same thing should be the same thing that I use for x grid. Do the same thing for y grid also. That's y axis. Then x and y, that's this, equals to mesh the grid. That means join the axes together. That's what it does here. Let me not bore you with this old plotting of graph and likes. So then we call this function x and y. This is it here. Then we have plt.show. This plt.show means show the graph. So this is what we have. So it's not only enough for you to use Python to write code, Python for calculation. You can also use Python to plot graphs. Right? We can use Python to plot graph. There is no way when we are plotting our graph. That's why in projection I wrote projection 3D. If I didn't put 3D here, it's just going to draw me just like a normal random graph, just the type of graphs that are just like up, like from here goes this way, come down, go up, come down, down. This is what I'm just going to be having. But putting projection 3D makes it very, very clear for me to put here. So, and in conclusion, Python is not tired of creating scientific libraries yet. More libraries are coming in day by day. And people are coming into Python because of its transparency, its accountability, its collaboration, its impact, its skepticism, and the peer review. All right, that's why people are coming to Python. I think I've tried to explain it very well. I'm done.
Sashi.
Yes, Effie.
Good morning, Sashi.
Good morning. Good morning.
So I love the presentation. I gain a lot. So I want to, would you also share your slide? I mean, share the link to your slide.
Link to my slide.
Yeah.
Yeah, I can share you my slide after the
I'm
presentation.
broke out.
Hello, Samuel. Good morning.
Good morning. Who broke your heart?
Who broke my heart? Well, it was one Igbo girl, sha, but that's by the way.
Thank you.
Why did you ask me?
Your
Good morning.
explanation, your example was scary.
It was very, very scary. Well, it's a mathematical function we are working on. That's why I had to
Okay,
just do
yeah,
something
it
like
made the explanation, but I really understood about optimization, premature optimization.
yeah. Okay.
Sorry,
Well,
good morning.
good morning.
I have a comment. So nice presentation. Totally.
Okay.
You killed it. So this is for the general house is a suggestion. For laymen like us, yeah, that are not really into the technicality of these things. Just the way you give an example of the ladies and all that, yeah, it's really explained what you were talking about. So it is good if we adopt that so that we can relate it with things we are familiar with, things around us. Yeah, it will make us understand what you are explaining better, since we are not really into the technical field of your work. I don't know if you understand what I'm saying.
Yes, I understand you.
Yeah, so for people like us, I mean, this time again, so for people like us who are not really into the technical aspect of your field, if you can relate, I'm not just talking about your presentation, no. I'm talking generally, so that we will be able to understand better and engage with your presentations around tech generally.
All right.
All right, thank you.
Any other person, please?
Okay, any other question from anybody?
Actually, I'm trying to ask, like, what is Python really means for, like, what is it for? Python language, what is it for?
Python is a programming language for almost anything. Like the way we have JavaScript that has been used for JavaScript is used for front end, for back end, for machine learning these days, for data science these days. So we have Python for vast
What I'm
majority of.
asking is, like in PHP, you are sure that if you want to read a website or something like that, you can make it a PHP language. So, like, what kind of, like, what kind of app do you want to be that will make you use Python? Like, if you can use Python for building of a website or anything like I use PHP for, that's what I'm trying to ask.
Okay,
Like, the
okay,
main,
we can use Python for backend or building a website. I use Flask and I use Django to creating backend of a website. The same way PHP, I think they use Angular or something like that. So Python we can use, yeah, I think PHP use Laravel, yeah. Python we have Django and we have Flask for web development.
Okay, thank you, Shay, for the presentation. Please, is Femi the same thing as Oluwa Samuel, or is it Obafemi?
Yeah, it is Oluwafemi. Yeah.
I'm seeing two Femi here. Femi, probably this Obafemi.
Yeah, Obafemi is here too.
Thank you everyone for attending this small session. We are really sorry, Shay, for not being able to speak well in the presentation because of all that. But I'm sure you had a nice time. So, okay, this will be the end of the session now. Let us stand us. That's the thing. I wish everyone happy New Year. Bye.